Hi everyone. Today our group will prove that English is not context-free grammar by demonstrating the intersection of regular grammar and English is not context-free. In the earlier homework, we have shown that the language that is recognized by DFA could also be recognized by REX, and the language that is recognized by PDA could also be recognized by CFG. For now, given two language L1 and L2, which are respectively context-free grammar and regular grammar, we could easily compute a PDA-P for L1 and a DFA-D for L2. Now construct a PDA-P prime that is all states are all possible tuples formed by the states of the machine P and machine D. On top of that, the start state is the tuple containing the start states of P and D, and the final states transition functions are adjusted similarly. The stack and input alphabet will remain unchanged. In constructing P prime, we have created a PDA that recognizes the intersection of language L1 and L2, and since L is recognized by a PDA, it's also recognized by a CFG. This intersection of CFG and regular grammar is a CFG. In formal language theory, context-free language play a crucial role. We also introduce two regular sets, which can be generated by finite state grammar. Now let's explore the regular set L. Imagine L as an expression in English. Each expression begins with the women such that, followed by 0 or more occurrences of the men such that, then, she, and 0 or more occurrences of certain phases like Z, like give him to him, get him to this, give this to him, and lastly, give this to this. And L concluding with left is here. Now we will have like the first assertion. The intersection of L with English follows a specific rule, which are reading from left to right. The number of occurrences of this never exceeds more than 1. The number of occurrence of him. We define an abstract set A based on this rule. The rule involves the careful balance of occurrences of this and him. And now we will have claim 2. Here's where the things get interesting. Claim 2 declared that A is not a context-free language. Putting 1 and 2 together, we reach the compelling conclusion: English is not a context-free grammar, context-free language. Now let's see some example. Consider the following expression: the woman such that she left is here. This is an English sentence and belongs to A, satisfying the conditions. Let's break down the structure. The women such that, we have it as X, and we have no occurrences of the men such that, which are Y, and then following by she, and then we have no occurrences of the phase in set Z, and we have left is here, which is the W. The condition of A the number of occurrence of this should never exceed by more than 1 the number of occurrence of him. In this expression, both y and z have 0 occurrences, satisfying the conditions.
So now that we have set the stage for our proof, let's get into the meat of it. But first, we'll need to define a well-formed noun phrase. So an element of A has the property that within the part C of N, no initial segment CK of Z of N has more occurrences of this than it does of him. What this sentence is trying to say is that the way we have defined Z is a union of some phrases, right? Like gave this to this, gave him to this, and so on. A k-length segment of some Zn, if you take the number of this occurrences and the number of him occurrences, the number of this occurrences cannot exceed the number of him occurrences by more than 1. We're going to use this property later in the proof. And the second part is a matter of definition, that if Z, and here's a different Z, not related to the definitions we said earlier, but if you have an ordinary English declarative sentence that contains an occurrence of a third person pronoun that does not have its antecedent within Z, then N is any noun that agrees properly with the pronoun in number and gender, then the N such that Z is a well-formed English noun phrase. So what is this trying to say? That the noun, some noun, right? The man such that something something is a well-formed English noun phrase if the noun matches the pronoun in number and gender. And here we have an example of where we are applying this rule recursively. So you can apply this once, that the man such that I thought that something something, and you can apply this like n times. Here we have applied it 4 times. The man such that I thought that the book that you put on the shelf that I bought for him was interesting. Because of the parentheses, it looks a little weird, but otherwise it reads as a somewhat long and tedious but still grammatically correct sentence. Now, before we show that A is not context-free, we first need to, we are just going to show that A is not context-free. So here we have a canonical sentence of the language A: x, y to the I, she, z to the I minus 1, z, q, w. And these are the variables that we defined earlier. Now, if we remove one instance each of y and z, then you have this x, y to the I minus 1, she, z to the I minus 1, w. And it should still be a valid sentence because we have not violated any condition of occurrences of this and him that we said earlier. I told you we would use it later. If you remove x and w, then we have a valid phrase, noun phrase here. And then you can do a little bit of manipulation around center factors. And it's just a little bit of linguistic algebra here. And what you end up getting is here, part E, where y to the I, she, z to the I minus 1, zq is the center factor of A, our first sentence. This is a valid noun phrase, and F is a valid English sentence that we get by adding the word left at the end. So what the author is arguing here is that if we generalize sentences in the language A and do a set of manipulations, then we just find that, oh, these are context-free, right? Does not depend on how many Y and Z you have. There is no additional dependencies. So that's part 1. Part 2 is that the intersection of L and English does actually belong to A. And we only need to show that L intersect English is a subset of A. So for this, we use the fact that English does not allow something like vacuous quantification. In fact, most languages, natural languages, do not allow this. And what that means is, we define the N such that Z as a well-formed noun phrase, but it needs to be like well-formed. You cannot just add any noun and any pronoun. For example, every book such that it rains, or the man such that I saw Mary. These nouns and pronouns in these phrases don't agree, and these are not valid phrases or sentences. So every expression in L intersect English will have some N occurrences of Y, And each of these must be eligible to some occurrence of him so that we get a good match of nouns and pronouns. You can do a little bit of thinking and find that any expression of L intersect English will not only have as many occurrences of Y as of Z, but also as many occurrences of him, the word him, as of Y. And since we have constructed our regular grammar in a very balanced way, we will find that any k-length, initial k-length segment of Zn will have exactly a matching number of the word him as the length or repetition of Y. So now that we have shown that L intersect English belongs to A, we have our final argument where A is not a context-free language because context-free grammars cannot keep track of multiple dependencies. We have a canonical context-free grammar here, A to the n, B to the n, and you have one dependency there, and that the equality of numbers of number of A and number of B. But look at this language, right? You have another dependency here, which is that at the end you have A to the j, where there is some restriction on the value of j. If you had A star here, that would be fine because there is no dependency there, but we have a dependency here. So similarly for A, we have dependencies, not just one, but multiple, right? We must have equal number of the word this and of the word him. And we also have long distance dependencies around the matching of scale and segments of Z and the length of Y. So that is why A is not context free. There is also empirical evidence around how humans process languages and how long distance dependencies like WH questions and questions starting with which or what have too many dependencies for English to process, but this is our nice formal proof here. And with that, we have shown that English is not context-free, but many restricted parts of the English language and many other natural languages can be context-free, and we would like to discuss some parts of that.
On the counter arguments against the statement, English is a CFG or is context-free. And so while CFGs aren't powerful enough to cope with the syntactic structure of all the natural languages, they can definitely be used to handle and represent the syntax of natural languages like English. And so usually this manifests itself in some sort of tree-like structure that's governed by rules, and this is used to generate a lot of common sentences in English. And so I'm going to spend some time describing these trees and the rules that govern them and the nature of them, and then also talk about some of the parsing algorithms that are used to parse the CFGs. And so at the bottom of this slide here, you see a very simple example of a tree which can be used to model a structure in English, and usually it's going to be a combination of terminals and non-terminals, which I'll describe in greater detail later on. And it usually has a start symbol, NP. So NP stands for noun phrase, and usually is just a bunch of words that surround a noun. And so on the next slide here, you see two very easy examples of applications of these tree structures. So to get into more detail, usually you have, on the left-hand side, you can see you can start with a non-terminal S, which can be broken down into a noun phrase and a verb phrase, and then those noun phrases and verb phrases can be broken down further into nouns and verbs and prepositions. So on the left-hand side, you see that this is the grammar to generate simple sentences like a woman shoots the man or the woman shoots a man. And then on the right-hand side, you see a more robust example of this tree-like structure. And so you can see that it's made up of different terminals like nouns and verbs and different kinds of adjectives, pronouns, prepositions, conjunctions. And so this is good enough proof to show that by using a tree structure and rules, we can generate lots of the basic sentences in English that includes combinations of prepositions and adjectives and nouns and different kinds of verbs. And on the right-hand side, you can see a pretty simple tree that shows the destructuring of a common English sentence. I prefer a morning flight. And so these sentences are, there's 4 important structures to these sentences that are used to model English. So the first is the declarative structure, which is just a subject-noun phrase, which is followed by a verb phrase or a sentence. And then there's the imperative structure, which begins with a verb phrase and has no subject. It's used for suggestions or commands. And there's the yes-no structure, which begins with an auxiliary. It's followed by a subject-noun phrase or a verb phrase or sentence. And an example of the yes-no structure is, do any of these flights have stops? And then the last important structure has one nuance. So it's the WH subject structure, and there's also the WH non-subject structure. So the WH non-subject structure is just identical to the declarative structure, except the first noun phrase contains a WH word. So WH word is something like which or what, why, and so, yeah. And you can see the 2 examples of the subject versus non-subject. And then lastly, there are pretty efficient parsing algorithms that are associated with CFGs. And one of them is CYK, Koch-Younger-Kasami algorithm, and they're used to analyze and generate sentences in a systematic way. So the CYK algorithm specifically is a fundamental tool in computational linguistics, and it's used in lots of applications like NLP and syntactic analysis. And so CFGs have had lots of success in computational modeling and NLP, but despite covering quite a bit, parsers and basic sentence generation, and despite being infinite in scope, they don't cover all aspects of English, including some important ones like sensitivity and LDDs.